I was really excited a few days ago to share what I'm calling Ghostling, which is a demo showcasing the Libghostty CAPI. A lot of people were really shocked in a positive way of how far Libghostty has come in that I'm able to create more or less a fully functional terminal. It could run NeoVim, it could run any modern application here, it could run Claude Code. How I could do this in a single C file in less than around 500 lines of functional sort of C code. And people are excitedly picking this up and doing really cool things already. And one thing people notice, which I did try to make clear in the docs, is that I say that the API is not stable yet. And I want to talk about what that means. So there's two types of stability I'm talking about here. There's functionally stable and ABI, the application binary interface. And from a functional standpoint, Libghostty is very, very, very stable because the core logic of Libghostty has been powering the Ghostty terminal application for years. It is used by millions of people. It is super real world proven. It has bugs, of course. We're gonna fix bugs, but it is very, very stable. Then there's the ABI compatibility, which is application binary interface. If you don't know what ABI means, I do recommend pausing and Googling this. It's a whole topic, but the basic idea about it is it's the ability for me, with the C library in particular, to ship updates to it and to have differing versions of it and to have a program that compiles against it statically or dynamically continue to build successfully and run successfully. And from a C perspective, there's a lot of things you have to think about that break ABI compatibility. If you change the size of a struct, if you change the number of parameters to a function, if you change the return type of a function, these things break ABI compatibility. And so from a stability standpoint, I'm not yet ready to promise that the Libghostty CAPI is going to remain ABI compatible. However, I am doing a lot of groundwork in order to make it that way. I really want to make sure that when we tag a version of Libghostty, say we release Libghostty 1.0, we release in the future Libghostty 1.5, and whether the person on their computer has 1.0 or 1.5, when they compile an application, it's going to work in both cases. It might have different bugs, it might have different functionality, but it'll build and run. So I'm going to showcase some of the stuff we're doing about it. So to do this, I'm going to look at the Libghostty CAPI documentation. This is a public domain. You can visit it if you want. It's not search engine indexed on purpose because it's updated with the Git repository, and it just covers the CAPI, but it is fairly full featured, full coverage in terms of what it does. So I'm going to show some of what we're doing. So the first thing we're doing with regards to ABI compatibility is a lot of opaque pointers. An opaque pointer, for example, here's a terminal. This is the terminal subsystem. Here's how you create an actual terminal instance. If we click on what Ghostty terminal is, you could see it's just a pointer. And what this is called a bunch of different things depending on the context. Usually I just like to call it an opaque type. What that means is that if you can't see the value of the struct layout itself is undefined. And because it's a pointer to the struct, I could actually change the size of this at any time, change the actual layout, change the size of it at any time, because all you ever see in your program is a pointer to it. And the pointer remains 32 or 64 bits, depending on your platform. Libghostty does work on both 32, 64 platforms. So the size of this will never change, even if the struct itself goes from, 1 byte to 1,000 bytes to 200 bytes. It gives me a lot of power there. And that's really important. And if I go over to my actual Ghostty source code and look at what that ends up looking like, this is actually the internal struct that your program never gets to see, doesn't get to access. But we actually have the real terminal that we allocate internally, the Zig terminal, and then we have some other state. But I could continue to add more state here, remove state here, and that's okay. So that's one way we're thinking about it. We have a lot of opaque types. The downside of this is when you have an opaque type, you can't just update access the struct field. So we do have to add a bunch of getters, and you also have to allocate at some point. I mean, there has to be a malloc here. So It does suck compared to the Zig API. There's a little bit more allocation, but they're long-lived types that are very small. They're just pointer sizes. It should be a very, very efficient allocation. So I'm not too worried about it. So you do have to run like Ghostty terminal new, pass in your allocators, and then an out pointer. I don't want to like confuse anyone, but remember that Ghostty terminal is a type def to a pointer. So this is actually a pointer to a pointer. So we are populating that. But the type signature makes it look obvious because in the actual example code, I'll pull it up later. But in the actual example code, it's pretty clean how this looks. And then we have stuff like options. And we'll talk about some of that ABI compatibility. For return values, I'm as much as possible standardizing on this Ghostty result enum. This is an enum, and an enum in the C standard is equivalent to an int. I believe it's an int, signed int. So we have 4 values. I could add and remove values at any time and keep this. I should say I could add values at any time, keep this ABI compatible as long as I don't use these exact values ever again. So this maps to 0, 1, 2, 3. I can't reuse those numbers for different semantic meaning ever again. However, I could continue to add new values and code should remain compatible. So that's another way we're ABI compatible. Another thing I said with opaque pointers is you need getters. So we do have getters, Ghostty terminal get. This is a way to get data from a terminal instance. The way we do this is inspired by, I would say the biggest library, but a lot of libraries do this, is like curl. We have an enum of the possible data that you could retrieve. So here you get the X position of the cursor, total number of columns, the current active screen, and then I document through the enum what the output type is going to be. You can see here the output types, and then we have a void pointer, and you're expected to provide the correct output type. The downside here is that there's a few. This can't be well compiler checked. I don't know a way to make this well compiler checked that your type matches what the terminal data expects. It's C. You kind of get the safety you signed up for. And the second thing is we can't pass in any other data. The only inputs we have here are the terminal, this, the data key, and the output and the result. Like I can't parameterize this getter in any way. But we get a ton of upsides. The upsides is I could continue. This is an enum, and like the other enum, I could continue to add new keys here of new data to get, and it doesn't break API compatibility. Previous versions won't know about the new key. It'll just get ignored. Future versions that compile against an older version, Ghostty is robust enough to detect that you're using a key we don't know about and will return invalid value. Out of the result will return invalid value. So it's pretty much safe to pass anything you want into here. We need to make sure we never change this output type, of course. That's part of the API compatibility promise. But other than that, you could get it out, and that's a huge, huge benefit. So that pattern is used all over Ghostty, this sort of like keyed getter pattern, and that's for API compatibility. It's really to minimize the number of functions we have because functions are much harder to change. Let's see. And there's another thing I wanted to show. If I can move myself. Right. So in the render state, let's go back to RenderState here. The RenderState's an API that is used to build high-performance renderers using Libghostty. It does stuff like dirty or damage tracking. It's stateful. It's super fast. It's the exact same API that we build our renderers on that could update the screen in literally microseconds. It's good, but we need to think about API compatibility here. So let's go look at the functions. And by the way, here's what I'm talking about in terms of like the pointer types look fine. Like you just do a Ghostty terminal, you don't see a pointer, feels good. Terminal new, you pass in a pointer, but it looks like a single pointer because you're just updating what that terminal is. Any C programmer, even relative beginners, this is going to look really clean. So all the like pointer to pointer confusion is hidden from you, which is nice. Okay, let's go look at the API. Let's go look at the functions. So you're seeing the same patterns here that we have: new, output opaque type, getter, data void out type. Setters work the same way, but But then we see some stuff that's different. Okay, here's uh, the colors reader. Actually, this should probably be part of the Git, but before we fix that, here's the colors getter. It returns a ghosty state colors. Now, this is a struct. And with ABI compatibility, you have to be careful with struct because if the size of the struct changes, things end up breaking. And you can't, reorder fields. There's a bunch of limitations around structs. The trick that we're using with structs is we're using something I think people call it sized structs. Windows does this a ton. The first field in a struct, pretty much almost every struct in the libghostty API, unless it's a struct that I'm so confident will never change. And if we do have to change it, that means we're going to have to introduce a new function that takes it. That's how we'll retain compatibility. But for every other struct, we use size structs. The first field is the size of the struct. And because that size is populated by the program compiling against Ghostty, it's going to be the size the program knows about. And we provide a helpful macro in C to do this, Ghostty init sized. So here's an example. You just, to initialize any struct, that size struct, you just pass the type to Ghostty init sized, and it populates the size with the size of. And this is important because what Ghostty does internally is we check the size and we compare it to the implementations side, like the Zig side, the libghostty side. We compare it to the size we have. And if the program has a smaller size than we have, then we know that it's only aware of an older version. We don't know what version, but older. And based on the size, we can know what version. So for example, if we only start with background, foreground, cursor, and the size is, but we have all this, but the size is only up to here, we know it only knows about these three fields. And so we will be very careful never to read or write these fields because the other side the memory will get corrupted. If the size is greater than what we know about, we know that they're aware of a newer version than what's actually running. And the same thing, we'll be careful to only access the fields we know about. The limitation here is that we can only detect ABI changes through size changes. If we change the type but the size remains the same, you can't actually detect if things change. So you have to be really careful about that. And the second is, it's related to the first. You need to be really careful about how you're adding and removing fields. You basically, to be safe, can only ever add fields. That's just the simple way to describe it. It's more complicated than that, but it's a simple way to describe it. So that's what we're doing with all these structs. I guess another downside is you can't pass undefined sizes. You can't pass undefined, uninitialized would be the C term, structs into APIs because you have to always initialize the size field. If someone passes a nonsense size, then you're going to get some garbage back. It's going to be really dangerous. But again, we're in C. The safety is sketchy to say the least. And so I think that's all I could think about. Those are the primary ways that we're doing ABI compatibility planning for today. This is something I do want to promise at some point, but we're not there yet. But I did want to share this to give you some confidence if you are starting to build some wrappers and things like that, that there will be this compatibility layer. Before we do tag the initial libghostty release, I do plan on reordering some of these data fields, maybe changing their output types. I will make a final pass over everything to get it into the shape that I want for that initial like ABI compatible moment. But this is where we're at today.